Good afternoon, geometers. This is Ms. Backfish, and I am here to talk to you about segments in circles. Okay, so this is kind of a standalone topic. This is something that we talk about, which is about the lengths of the segments when we have segments that meet either inside or outside a circle. In other words, here I have two segments that are both chords, and they meet inside the circle. So that's one case we're going to look at today. The other is if I have two segments that meet outside the circle. So these are both secant segments. And we're also going to talk about tangent segments. Well, so this is really the two categories we're going to divide these up into when we talk about segment lengths with these chords and secants and tangents. We're going to talk about when they meet inside the circle. So these meet inside the circle. And I want to make that pronounced. And it doesn't look that red on film, but there we go. And here we meet outside the circle, and that's what's kind of most important to us about this one. Okay, so first off, let's remember that we've seen pictures like this before, and we weren't talking about segment lengths. Here I'm talking about the lengths of these pieces. Like how long is that part? How long is this whole segment? How long is this part? Same thing here. Talking about lengths from here to here or here to here. Before, we've had pictures like this where we were talking about angle measures and arc measures. So it's important to recognize that this is different from that. Do you see how there are degree symbols on all of these? That's a big hint. This is about the angles and the arcs. Both of these pictures are. See the degrees? That's what that's looking at. We won't be dealing with degrees here because we're talking about length of segments, not angles or arcs. Okay, so we have little kind of mnemonic devices that we use for both of these to help us remember how these segment lengths are related. And when they meet inside the circle, the little device we use is part times part equals part times part. And let me explain that because it sounds like you're just multiplying the same thing over and over, and you're not. One part times the other part of one of these chords. So for instance, this part here times this part here. That's what one side refers to. One part times the other part of the same chord equals, then we go to the other chord. One part times the other part of this chord. So none of these, when we say the word part there, none of those mean the same part. So one part times the other part of one chord equals one part times the other part of another chord. And we could add that if we wanted to on there. I just threw it in real light there. It's not really the main thing we have to think of, but part times part of one chord is equal to the part times part of the other chord. Let's use some variables to stand for those lengths. I'm going to call this part A and this part B, meaning A is the length of this portion of that chord, and B is the length of this segment in that chord. And then I'm going to come over here and I'm going to call this C and this D. And then now we can rewrite that sort of little device there. We could say, using this, what I'm saying is that A times B has to equal C times D. And really, this is just another way of saying the portions, the parts of these segments are proportional. Okay, we're going to come back to that in a second and do some examples with that. Actually, let's go ahead and do it now. First example, I have two chords. They meet somewhere in my circle, and we're never implying that they have to meet at the center or anything like that. They can meet anywhere. They meet somewhere in my circle, and I know parts of the lengths of these pieces, but one's missing. Well, so part times part of one chord. Well, that would be like 9 times 5 equals part times part of the other chord. So that's 15 times x. 9 times 5 is 45. 15 times x is just 15x. And then I divide both sides by 15, and I get that x is 3. And if x is all I need to find, then I'm done. Sometimes I might need to go back and plug in or something like that. Okay, so these two segments meet inside the circle again, and so when they meet inside, this is my rule. Part times part of one equals part times part of the other. So I can write an equation that says this part, FB, times this part, BD. So the two parts of chord FD, which is 2x times x, is the same, equal to, the two parts of chord AC, AB times BC, 6 times 3. And sometimes we want to write it out like that, so let's do that. Let's say FB times BD equals AB times BC. Okay, so what is x times x? It's x squared. 6 times 3 is 18. So now I need to get the x squared part alone before I worry about getting x alone. And that gives me this. Take the square root of both sides to get x alone. And I get x equals plus or minus 3 is really what I get. But is it really plus or minus 3 here? No, because I can't have a negative length. The length of BD can't be negative 3. So really it's just 3. Okay, so x equals 3. Now what if I was asked not to find x here? Because every time you find x, you go back and say, is this what I was asked for? What if I was asked to find FD? Well, that means the length of segment FD. So I would have to plug in the 3, and I would get 3 here, and plug in the 3 here, and I'd get 2 times 3, which is 6. And I would say this part is 6, this part is 3, 6 plus 3 is 9. And I would be done. All right, last one's a little bit more algebraic. I just wanted to remind you of one little part about how you do this. Still same thing. These are very straightforward. It's really just part times part equals part times part, piece times piece, however you want to think of it. So 8 times 4x plus 2 equals 9 times 4x. So that's the geometry, is the setting it up. We know that they're proportional, so we can set it up this way. The rest is the algebra, and the algebra can sometimes be a little bit more complicated. It is here. You have to remember that since there are two terms here, 4x plus 2, you have to multiply the 8 times both of them. That's distributive property. That's why I used parentheses, to remind myself of that. So 8 has to be multiplied times the 4x, and the 8 has to also be multiplied times the 2. And that's what I get. And over here I have 36x. I'm going to subtract 32x from both sides, and I get 16 equals 4x, and x equals 4. And again, I would stop and say, oh, do they need just what's the value of x, or do they need me to plug in and find out that this would be 4 times 4 is 16, or that this would be 4 times 4 plus 2, which would be 18? What do they want me to tell them? But that's how we do it when the segments meet inside the circle. Okay, so we got this down. What about when the segments meet outside the circle? And that could happen when they're both both secants, or both, one's a secant, one's a tangent. Technically, you could think of it as them both being tangents too, but we kind of already have a rule that applies there. So this is how this one works. First, I'm going to tell you the kind of rule, the way we write it. We say the outer part times the whole thing equals the outer part times the whole thing. What does that mean? Well, the outer part of one of these segments. So we have a secant segment here. The outer part means the part that's outside the circle. The whole thing means the whole thing, including the part that's inside and the part that's outside. So that would be my outer and my whole. Then if I look at the other secant segment over here, the outer part is just this piece right here, the part that's outside the circle. The whole thing it includes that part and the part that's inside the circle. So let's go ahead and give this some letters and talk about it that way. Let's say that this segment, I'm going to use purple. Let's say that this little segment here is A, and this is B, and this is C, and this is D. And those are the lengths. Okay? Now, the outer part, let's start with the blue one. The outer part of that blue segment is the part that's labeled A. The whole thing, and there's a reason I use parentheses, is A plus B. When we have two pieces that make up a whole length, we add them together. Don't multiply, add them together. So the whole thing is a plus b. And the reason I used parentheses is because that's going to have to be distributed. That's how we multiply one term times two terms. All right, so let's look on the other segment. The outer part is the part outside the circle, that's C. The whole thing is C plus D. Don't put CD. That means multiplication. We're adding. This is something people tend to get wrong pretty frequently, is they want to multiply these parts to get the whole length. But if I have a segment, just any random segment, and it has two parts, and I asked you, what is the length of that whole segment? You would say, oh, that's 9 because I do 2 plus 7. Well, don't forget that when you're doing these. To get the length of the whole thing, you want to add, not multiply. Okay, so here I have some segment lengths. There's no degree symbol in sight. We're not dealing with angles and arcs. These are lengths of pieces of lines. Okay, so I need to find out what x is. So I see that these meet outside the circle, and I say, okay, then this is the one where the outer part times the whole thing on one of the secants equals the outer part times the whole thing on the other secant. All right, so for our problem here, the outer part on the top segment here is 4. The whole thing is not the 18. The whole thing is 4 plus 18. 4 plus 18 is 22. So that's where that 22 comes from, is adding the 4 and the 18 together. Then on the other segment, the outer part is 6, and the whole thing, this is where the mistake sometimes comes in, the whole thing is not 6x. Don't say 6x, because that would be multiplying these. The whole thing we're adding is 6 plus x. Would it be easier to solve if it was 6x? Sure, but that's not what it is. Okay, so here's my equation to solve. So 4 times 22. 4 times 22 is 88. And then on the right-hand side, I have to distribute. 6 times 6 is 36. Let's break this over here. And 6 times x is 6x. So that's how this equation simplifies first. Then I'm going to subtract both sides, 36 from both sides, and that gives me 52 equals 6x. Divide both sides by 6, and it's not going to go an integer number of times because 52 is not a multiple of 6. That's going to be 8, because 6 times 8 is 48, with 4 left over. So 4 over 6 is 2/3. Or I could say that that's just, and simplify this, what goes into both of them, 2. This is 26/3. Or I could write it as a decimal. But that's my answer. Again, every time you solve for x, go back and check your problem and make sure you're not asked, what is this whole length or something like that. Make sure you don't have to plug in. All right, next problem. This is the first time we've done one like this. What's different? This is not a secant. That is a tangent. Okay? It does not come back into the circle. They still meet outside the circle though, so we're still going to think of it the same way. For simplicity's sake, I'm not going to think of it any different when we have two secant segments like up here versus a secant and a tangent. I'm going to think of it the same way. It just takes a little bit of adjustment of my thinking, not much. Okay, let's say I've got a secant and a tangent. All right. And here I only have 3 pieces, so let's call them K, M, and I don't really want to use N. I don't know why. Let's use T. Okay. We can still think of it in terms of this. Here's the difference. For a tangent, the outer part, in other words, the part outside the circle, is the whole thing. So these two are the same. So when you multiply outer part times whole for t, that's multiplying t times t. It's multiplying it times itself. In other words, outer part times whole up here would be k times k plus m. Outer part times whole for t is just t times t. So that ends up being squared, basically. That gives me a t squared. So let's go back to our problem and apply that. So same rule, just applied a little bit differently. Outer part times whole thing. That's going to be 4 times the whole thing is add 4 times 4 plus 5. 4 plus 5 is 9. Okay, we could write that if we want to, 4 plus 5. That's where the 9 comes from. And on the other side, we have x for the outer part, and we have x for the whole thing. So x times x. So 4 times 9 is 36. X times x is x squared. And then we have to take the square root to solve. Find a different color here. And since x refers to a length, it can't be negative. So I'm not going to worry about the negative here. So positive 6 equals x. And I've got my x. So we're using the exact same rule, even when it's a tangent. It's just that we end up, when we do outer part times whole thing, multiplying the segment times itself. So if you go, well, wait, the outer part is the whole thing? Cool, multiply it times itself. Okay, I saved the best for last. This can happen whether it's two secants or a secant and a tangent. And what the this I'm referring to is, what can happen is, what if my variable or a variable expression is in the outer part? Watch what happens. When I do outer part times whole thing, this is x is the outer part. The whole thing is not 11x, it's x plus 11. Add them together. Equals outer part is 6 times 6 plus 15. What's 6 plus 15? That's 21. I'm just going to put this in case somebody's like looking at this and saying, where did that come from? Okay, so now I'm going to go ahead and distribute over here. And when I do, I get x squared and I get 11x. This is not going to be an equation that I can simplify by taking the square root. And 6 times 21 is 126. This is going to be quadratic. That's what happens if your x is outside, if it's the outer part of the segment. Just like here, when my x was outside, I got a quadratic. But this quadratic that I got up here was able to simplify pretty quickly because I could take the square root. Here I can't. When you have a plain x, an x to the first power, a linear term, you can't simplify just by taking the, or you can't solve by taking the square root. Instead, we're going to have to go ahead and move everything onto one side, which is what we do if we're trying to solve a quadratic any other way other than taking the square root. And now I'm going to try to figure out whether or not this can be factored, or maybe if I want to use the quadratic formula. In order to see if it can be factored, I need to know if there's two numbers that multiply to give me negative 126 and add to give me 11. So think about that for a sec. So basically, I played with my calculator for a little bit and said, oh, there we go. 126 divided by 7 gives me 18. I just played around with numbers that might go into 126. And 7 and 18 are 11 apart from each other. 18 minus 7 is 11. So that's what it's going to be. So 18 plus negative 7 gives me 11. So that's going to be the negative. And then my factored form is x plus 18, x minus 7. To solve a factored form, you set each one of them equal to 0 and solve. Does x refer to a length here? It does. So this isn't going to work. We're not going to have a negative x. So it's going to have to be this other one, which gives us what? X equals 7. And that's my answer. Don't forget to go back and look and to say, hey, did they ask me for just x? Or maybe did they ask me for this whole length? What if this was like CD and they wanted me to find CD? Okay, then I would take my 7 that I just found for x, and I would say 7 plus 11, that's 18. Hope this has helped. See you next time.